Welcome back. We're in chapter 15 on oxidation and reduction. And in this section, we're going to look at what could be very obvious or very hidden, and that is what's an oxidation number. Oxidation numbers really are used in order to determine whether something has been oxidized or whether something has been reduced. A lot of the oxidation numbers you actually already know. Anything that you would look at the periodic table and say, what charge would group 1 be, or what charge would group 7 be? When you're looking for those charges, those are called oxidation numbers. So many of these you can almost pick the entire periodic table and know what they would likely be. Now, you're going to see some rules here that will help you to assign proper oxidation numbers. And then as those oxidation numbers, the ones from the rules, the other ones are easy to kind of pick out. So there's some that will change all the time and some that won't change at all. So depending on, do the easy stuff first and then leave whatever's left, and that becomes the oxidation number. I'll show you some examples. Here are the rules. The first rule is that every molecule is neutral. So if I have, for instance, sodium chloride, I have a positive charge in the sodium, I have a negative charge in the chlorine, and I may not know what the charges are, but I know that the positives and the negatives will cancel each other. They always cancel. So electrically, positive and negative wise, they always equal zero. A molecule always equals zero, or a compound, whatever you would look at it and you see I've got more than one atom in this stuff. You're always going to, if there's no charge listed, it's going to equal zero. Okay, so if you know some of them, you could figure out others simply by adding it to whatever the number is to make you zero. That's a really great, easy way to do it. So the oxidation number of any element is also zero. So if you have, say, zinc, or you have chloride gas or hydrogen gas, any of the diatomic molecules like hydrogen, oxygen, nitrogen, or the group 7 halogens, where it's like Cl2 or Br2, those are always going to be zero. If you have just copper, metal, or silver metal, or something by itself, that's always going to be zero. So that's really easy. It's a give me. The other one is if you have an ion, like if you do have a polyatomic ion, whatever the charge that you memorized of that polyatomic ion, that's the charge. So if you have nitrate, NO3, the charge of nitrate is -1. And so that particular thing will not equal up to zero because it's not a neutral compound. It's a polyatomic ion, which means they will all add up to whatever that charge is. So in the case of nitrate, NO3 equals -1. SO4 is -2. Anything that we did when we were looking at the polyatomic ions. Number 4 is very simple. Anything in group 1 is +1, including hydrogen. Anything in group 2 is +2. Continuing, we see that fluorine is always -1. Group 7 often is -1. We're going to see that very common. Group 1 that's almost always done is oxygen. You're going to have so many oxygen reactions. In fact, this is called oxidation, named after oxygen, because oxygen is an incredible oxidizing reagent that causes things, it steals electrons from everything. As that happens, it turns from oxygen gas into an oxide, like a tarnish, so like a silver tarnish or a rust or something like that, or a spoilage. All of this is happening with oxygen, and there's other things that can steal electrons, but oxygen is a terrible culprit, usually very guilty. And so oxygen is always -2. Okay. And then the last one is hydrogen. Hydrogen, you can almost guess 100% of the time is going to be +1, unless it's acting with a metal, and it will always be in the second place. If it's like lithium hydrogen, then it's lithium hydride, and hydride is when hydrogen is a negative charge rather than a positive. Okay, so these are the rules, and they're not very many rules, and a lot of these rules you are like easy to guess. You could almost guess these because of what you know from the octet rule. So here's some examples. if I have magnesium chloride, chlorine is in group 7. That means it's in order to have an octet equal to group 8, it needs to steal 1. So group 7 is -1. There are 2 here in the chloride. There's 2 chlorines here, so that means this side of this molecule is -2. And to balance it to equal 0, this is going to be +2. Another way to guess this is magnesium is in group 2. It's in the second column, so it will always be +2. So here's +2, this one's -1. Now look here carefully. This is not -1 times 2. We're only looking at what's the oxidation number of chlorine. It's -1. What's the oxidation number of magnesium? It's +2. In carbon tetrachloride, chlorine is again -1. There's 4 -1s. So what balances with 4 -1s? 1 +4. So +4 is a carbon, 4 -1s as chlorines. Here's a polyatomic ion. So this whole thing has a charge. So it doesn't add up to 0 in this case. This adds up to -3. So what we know is we know that oxygen is -2. I don't know what phosphate is. It could change depending on what it's joined with. So lots of these other elements can change when it's in a compound. So figure it out. Go with what you know and then figure out what you don't know. So I know that -2 is oxygen. And in this particular polyatomic ion, there's 4 of them. So 4 2s is -8. On this side of this molecule, I've got -8 charge. What balances it? Now, if this were a 0, I would need a +8. Phosphorus would have to be a +8. But I don't want it to add to 0. I want it to add to -3. So what number -8 is going to give you a -3? Well, 5. A 5 minus 8 is -3. So in this case, phosphorus is +5. And we already memorized that oxygen was -2. And I'm not trying to multiply it. It's not going to be 2 times 4 or whatever. Oxygen is -2. So -2 is the oxidation number of the oxygen here. +5 is the phosphorus. Okay. So you're always wanting to know which one was oxidized. Which one got the electron stolen? Who is the victim? Okay, and who is the culprit? The victim had electrons stolen from him and he becomes positive, more positive. And you want to know how much was stolen. Was 1 electron stolen and he becomes more positive by 1? Or was 2 electrons stolen and he becomes more positive by 2? And because we want to know where the electrons are. As you're accounting for them, where did they go from and where did they go? And those are the questions you want to know in a oxidation reduction, or also called redox reaction. Okay. In the example of iron metal is from the periodic table. It's a 0. Chlorine gas, even though it's got a 2 here, this is one of the diatomic molecules. Remember hydrogen, oxygen, nitrogen in group 7. This is one of the group 7 ones. This is 0. Okay, it's not a compound. This is a compound. Iron chloride is a compound. This is chlorine is -1 each because it's in group 7. Iron, now, I don't know what it is. It could be multiple things. So I figure it out based on what I know. I know that this is -1. There's 3 -1s. So this has to be +3 to balance with -3. Don't worry about these coefficients. That's simply a balanced equation. I'm looking at the compound itself. It has to equal 0. So if I've got 3 -1s, I have to have 1 +3 in order to balance it. Okay, because I don't have a subscript here, so I've got 1 molecule. It has to have equal charge opposite to these 3 -1s. So it has to have a +3. So if the iron went from iron 0 to iron +3, that's been oxidized. And the only way that something can become positive is by losing its electron. So it lost 3 electrons. The chlorine went from 0 to -1. That means it was reduced. It went down in charge, but it only went down by 1. So what's going to happen in order to go up 1, 3, I'm going to need to go down 3 -1s. Like it dropped by 1, but I need 3, and that's what's happening here. You're going to have coefficients. The balanced equation The reason it is balanced is because the number of electrons stolen has to equal the number of electrons gained. So if it only goes up by 1, but the other one went down by 3, then you're going to have to multiply to figure out how many molecules are we talking about that went up by 1 in order for another one to go down by 3. And so a lot of times that's what the math is. The math is simply figuring out how many different molecules are involved. So very obvious, reduction is reducing. It's going down in charge. It's going down in charge because it stole an electron and it becomes more negative. If you're oxidized, you go up in charge because you have an electron stolen from you. Here's another example. Magnesium is positive 0, right? Because it's not a compound, so it's not positive or negative. It's just an element, so it's 0. Chlorine gas is also 0 because this is diatomic element. This is a compound because they're acting together. So the first one is positive, the backside is negative. So let's start here. This is 0 and 0. What is this? Chlorine, if it becomes oxidized, becomes positive, negative? Becomes -1 because it's in group 7. So there's 2 -1s. So to balance with 2 -1s, I have to have 1 +2. So now that I know charges, I can see which one went up and which one went down. Magnesium went from 0 to +2. That's oxidized. It went up in charge. The chlorine went from 0 to -1. Because remember, not that there's 2 here. There's 2 here to make a -2, but each one was -1. So it went from 0 to -1. That means it was reduced. It's the culprit. It stole the electron from the magnesium and turned magnesium into a compound. Okay, so knowing which one was the oxidation, which one was a reduction. Okay, so what happened is magnesium had 2 electrons ripped off. So you can think of it as magnesium. Here's the magnesium with the electrons, and here's the magnesium without the electrons, and then here's what's left over is the electrons. So when you're doing a reaction where you're actually balancing it, you need to account for the electrons left and account for the electrons gained. You want to know where they came from and where they're going. And we'll talk about that when we balance them in the next section. So here's a final example. You've got iron, which is just metal, so that's a 0. You have silver, which is just a metal, that's 0, so this is 0 and this is 0. We know that just by looking that there's nothing with it. You've got silver chloride here, that's a compound. So chlorine is -1 because it's in group 7. Silver was one I memorized as +1. So this is +1, -1. Iron, I have no idea. So I'm going to have to go with the chlorine first. Chlorine is in group 7, so it's -1. That means that the iron has to balance that, so there's 3 -1s. So this has to be iron 3 chloride, so it's a +3. So I've got 0, 1, -1, +3, -1, and 0. So I'm looking to see which one went up, which one went down. So iron went from 0 to +3. They're written here in case you want to see it, 0 to +3. And so it went up, it was oxidized. Iron is oxidized. How much did it go up? How many electrons were stolen? It turns out that it went up from 0 to 3. That's a 3 difference. That means 3 electrons were lost. Silver went from a +1 to a 0, so it dropped 1. But we have to account for every electron. So if 3 electrons were stolen, but only 1 electron was gained, what that means is I have to have more than 1 molecule of this so that each one that was gained will equal what was lost. That is an accounting that has to be figured when you're doing oxidation reduction. How many went up? How many went down? So if one of them went up by 3, the other one went down by 1, I must have 3 molecules. I have to have 3 of these silver chlorides to turn into 3 silver molecules, or 3 silver atoms. So what you're going to see on the last part is that in order to balance it, I have to multiply the one that only dropped by 1 by 3 to make up for the 1 that went up by 3. Okay, so that what's happening is 3 went up and 3 went down. Okay, I stole 3 from the other, so he lost 3 and I gained 3 because I'm reduced. And then you figure out all of the other ones, making sure that it's balanced. It's a different way of doing a balanced equation. I really hope this helps. I know this is hard, but just see me in class and I'll try to help.